Hello everyone, we are Team Interplanetar, a multidisciplinary student robotics team from Bangladesh University of Engineering and Technology, presenting our latest rover, Prochesta 3.0 for ERC 2024.
Mechanical Design and Manufacturing Subteam is responsible for design, simulation, and manufacturing of all the structural components of the rover. This subteam is divided into 4 divisions for effective task distribution: robotic arm, chassis and suspension, wheels and steering, and science tool. About 30 members work under these 4 divisions. Moreover, each division has its own project leader who report to the subteam leader.
In electrical subteam, we focuses on electrical circuit designing, PCB manufacturing, and wire management. Our subteam consists of 12 members, which includes 4 subdivisions. They are wheel board, science board, arm board, and power distribution board.
Scientific Analysis Subteam is responsible for geographical and chemical analysis of soil sample for determining habitability, extent, and extent life. The subteam comprises of 3 divisions, namely Chemical Analysis, Geographical Analysis, and Module Testing. There are 8 members in total. Each division has a separate project leader who report to the subteam lead.
Documentation and outreach subteam might not be on the front lines of building the physical project, but we are the backbones that makes it all possible by providing logistical support, managing sponsors and finances, and presenting the team vibrantly through multiple media platforms. Despite our diverse roles and responsibilities, this subteam of 14 people work seamlessly together with technical team to achieve team's overall goals.
The software team is responsible for developing the software of the rover and operating the rover. We have 11 members organized in 5 different subteams for effective task handling and specialization. The subteams are autonomous navigation, manual teleoperation, arm kinematics, drone, and graphical user interface.
While space exploration may not be an immediate possibility for Bangladesh, the groundwork can be laid for our future endeavors. Our team from here is determined to make its mark, brimming with curiosity and a yearning to explore the cosmos. Here, robotics is a developing sector. We have been participating in ERC since 2015 and delving deeper with our innovations for both remote and on-site editions. In 2022, we participated in ERC with our Rover Renaissance version 2, where we achieved 8th and 4th positions consecutively in on-site and remote edition in the same year.
A lightweight, four-wheeled rocker suspension mechanism with bar differential is implemented. Both the suspension and chassis are made of TIG-welded stainless steel square tubes. As per ERC requirements, the rover can move forward and backward, can turn left and right. The rover can also drive on slopes and so on.
For safety, a high current relay operates with a key switch which can trigger both manually and remotely from the base station, allowing immediately stop the rover in case of any emergency.
The system allows the rover to traverse through rush environments. It can climb over rocks and uneven sandy grounds.
We have designed a centralized power distribution system to provide various voltage output to various components like antenna, motor, servo, and other sensors. Our custom-made PCB can handle high current up to 100 ampere.
This comprehensive design addresses the power requirements and includes crucial monitoring and safety features for the rover operation. An addressable RGB LED stripe mounted on a stand in the top of the electric box is being utilized as an activity indicator of the rover operation modes.
The rover arm is manufactured using TIG-welded stainless steel parts. This year, we have simplified our arm from a 6 degree of freedom design to a 5 degree of freedom design for simplified control and vibration reduction. Each joint has a magnetic encoder for precise movement, and inverse kinematic system is under development. We have manufactured the wrist using aluminum and 3D printed parts to make it lightweight. By removing the yaw movement, we could reduce the size of the wrist by 33% than previous year. We have also made improvements to the end effector, resulting in better roll motion and a more compact design. With the aid of an onboard camera, the end effector can push buttons, flip switches, plug in USB, and type on keyboards. With the 360-degree continuous rolling, we can turn knobs and drive screws with a screwdriver. The arm can pick up objects from the ground, pull ropes, open and close latches and drawers. It can also perform ERC tasks like picking up probes and building walls with blocks.
For ERC 24, we have designed a compact yet powerful science module which is 34 cm long and 26 cm wide with a 7.5 kg payload capacity.
Lightweight aluminum frame minimizes overall weight, while high-strength stainless steel is used in critical guides and moving parts, ensuring smooth operation.
For soil collection, we have an auger drilling mechanism capable of extracting soil from the depth of 30 cm. Both auger drill and soil storage descend to the soil surface utilizing a two-step lead screw mechanism. Upon completing drilling operations, Soil ascends to the uppermost level of the storage platform, aided by the drill and cylindrical pipe assembly. After reaching this elevation, sample soil is deposited into the storage positioned beneath the drill platform. Though the centrifugal force tries to spill out soil samples, but the funnel housing prevents it and helps soil to drop into the storage perfectly.
We are using a custom user interface connected to ROS to perform manual operations with the rover. The rover operator can manually control various functionalities of the rover using this interface. Additionally, a USB joystick can also be used for navigation and executing pre-programmed operations. We are using WebSockets for streaming the video feed from the rover to the base station with low latency. A separate user interface for the camera feed makes it convenient for the operator to monitor the rover throughout the tasks. We have set up a 2.4 GHz communication link between the base station and the rover using two Rocket M2s. We are using a 120-degree 15 dB sector antenna at the base station and a 13 dB omnidirectional antenna on the rover. These are high-gain antennas that ensure no line-of-sight communication between the base station and the rover for up to 1.5 kilometers. The overall communication system of the rover weighs under 3 kilograms. The base station equipments, including the sector antenna and the additional hardware, weigh under 5 kg. This makes the system portable and easy to assemble.
For droning subtasks, we are using the optional DJI drone to navigate to the Argo tag's position. We are developing our algorithm to detect the Argo marker and navigating to its position in simulink.
The drone will navigate to the Argo markers in an orderly manner. The algorithm can distinguish which Argo marker should be traversed first. When reaching the tag, the drone will continue its search for finding the next target Argo markers. Upon reaching a tag, the drone will capture an image. When droning task will be finished, the drone will land.
For the navigation subtask, we are implementing autonomous movement algorithm for the rover. We are utilizing the Stereolab Z2 camera for visual odometry and Argo marker detection. The rover can detect Argo markers and navigate to the marker's location autonomously.
Our rover also can follow a moving Argo markers. As the image processing is done on board, the rover processes the image frame and reacts to the corresponding commands quickly for following the Argo marker. Our rover will navigate to the Argo marker in an orderly manner. The algorithm can distinguish which Argo tag in the frame should be visited first.
We are grateful to our sponsors and partners for their continuous support. Thank you for watching. See you in ERC 2024.